We've all seen the familiar planetary group illustrations in textbooks, with the Sun appearing somewhat larger than Jupiter. However, this depiction doesn't accurately reflect the true scale. The Sun is so massive that you could fit around 1,000 Jupiters inside it. Yet, despite its size, our Sun isn't the largest star in the universe or even within our galaxy. That title goes to U.I. Scott, and compared to it, our Sun seems like a small pebble. But there's an even more stunning discovery that scientists have made by accident: a mysterious ancient star with a black hole inside it. This cosmic enigma is not only perplexing astronomers but also holds the potential to reveal crucial insights into the origins of the universe. But how can a black hole exist inside a star? Why were these stars so enormous? And what would happen if a black hole star wandered into our solar system? Stars, like celestial blacksmiths, forge most of the elements in the universe within their fiery cores. However, the stars that may have existed at the very beginning of the universe were vastly different. Instead of typical stellar cores, these stars harbored black holes at their centers, allowing them to grow to enormous sizes, far beyond the capabilities of normal stars. Stars are born from vast clouds of gas and dust, with gravity causing the densest regions to collapse. The resulting mass heats up, forming a protostar in the early stages of stellar development. Over time, this hot core accumulates more material from the surrounding gas, eventually becoming a main sequence star that generates energy through nuclear fusion. Our Sun took about 50 million years to reach this stage. Most stars will spend the majority of their lifetimes as main sequence stars, but eventually, they will either become white dwarfs if their mass isn't large enough, or undergo a supernova explosion. After a supernova, the remnant can either become a black hole or a neutron star, depending on the star's mass. When our Sun runs out of hydrogen in about 5 billion years, it will expand into a red giant, growing up to several times its current size before shedding its outer layers and becoming a white dwarf, an incredibly dense object roughly 200,000 times denser than Earth, but about the same size. The surrounding solar system will cool, with temperatures plummeting to around 18 million to 10 million degrees Celsius. Over the next 10 billion years, the white dwarf will solidify, similar to how water turns into ice, although in this case, the material will be carbon and oxygen. Stars that are more than 10 times the mass of the Sun have a different fate. They are massive enough for their cores to collapse after supernova, but they lack the mass needed to become black holes. Instead, the pressure inside these stars compresses protons and electrons so tightly that they combine to form neutrons, and the star becomes a neutron star. Neutron stars are among the densest objects in the universe, second only to black holes, with a size similar to a small city, about 12 to 20 kilometers in diameter, but with a mass comparable to that of the Sun. A chunk of neutron star material the size of a sugar cube would weigh around 1 billion tons, roughly the weight of a mountain. Now, how do some stars become black holes? During a star's active life, two opposing forces, nuclear fusion and gravity, work against each other. Nuclear fusion generates energy, while gravity pulls the star's mass inward. Once the star runs out of fuel for fusion, there is no longer a force to counteract gravity, and the star collapses in on itself, much like the controlled demolition of a building. Einstein theorized that anything with enough mass and compacted within a certain radius could become a black hole. Over time, black holes continue to grow by consuming nearby material. As they do, their gravitational pull becomes so strong that nothing can escape, and their event horizon expands. This process is similar to the sinking of the ground due to the collapse of underground structures, but with black holes, it's a gravitational sinkhole that rapidly grows as it pulls in more material. Most black holes have a limit on how quickly they can grow, known as the Eddington limit. This is the point where a black hole can no longer consume material faster than it currently does. Imagine filling a tire with air, but the tire has small holes in it. As the pressure inside increases, some air escapes. Similarly, as matter spirals into a rotating black hole, it speeds up. Around 42% of this matter is converted into energy, creating powerful radiation that pushes some of the incoming material away. This process is so efficient that the energy released by the black hole exceeds the energy produced by nuclear fusion in stars. Now, imagine a future where we could harness this energy for practical use. Some of the largest black holes, with massive surfaces that attract matter, also have this limit. These supermassive black holes are found at the centers of nearly all galaxies, and some are even bigger than we thought. Their immense size remains one of the biggest mysteries in cosmology. The gradual accumulation of matter throughout the universe fails to explain their massive size, but one possible solution might be black hole stars or semi-stars. These ancient cosmic objects could have been the largest stars to ever exist, even larger than the biggest black holes we've discovered so far. While current conditions in the universe don't allow for the formation of such stars, in the early universe, space was filled with enormous gas clouds. In these dense regions, material collapsed under its own gravity, forming child stars of exceptional size. Some of these stars might have originated from dark matter halos, massive, invisible regions of dark matter containing up to 100 million solar masses, where thousands of incredibly massive stars could have formed. Normally, large stars would undergo a supernova and leave behind a massive black hole. However, these ancient stars were so enormous that their size allowed them to absorb the intense forces that would normally blow off their outer layers during a supernova. Instead, these stars underwent a collapse that left a small black hole at their core, while their outer layers remained intact. If you could somehow observe this process from a distance, you wouldn't notice any changes in the star itself. Once a tiny black hole forms within a star, it begins consuming material from within. Although the black hole is small, its rotation causes the surrounding material to spin at nearly the speed of light, forming an accretion disk. The friction in this disk heats the material to extreme temperatures, emitting massive radiation that causes the star to shine like a small galaxy. Semi-stars, if they existed, could have grown faster than any black hole we've ever observed, eventually surpassing the size of the largest known stars and black holes like Stephenson 2-18 UI and T618. These stars could have grown to sizes many times larger than the Sun, possibly even reaching the size of our entire solar system or beyond. But with such immense size and mass, these stars would have exerted incredible gravitational forces that led to their eventual collapse. As stars become more massive, their life expectancy decreases. Our Sun, for instance, has been around for over 4 billion years and has approximately 6 billion years left. In contrast, the life cycle of dark star-like objects is much shorter, lasting only 2 to 3 million years before they dramatically explode, forming an enormous black hole that is hungry for more matter. This black hole will float through space, consuming anything in its path. But what if such a star wandered into our solar system? The gravitational pull of a black hole could cause chaos in our once stable planetary system, disrupting the orbits of planets and other celestial bodies. The consequences would begin before the star even entered our system. As it devoured the outer planets and other objects, the temperature and luminosity of our solar system would rise drastically, making Earth uninhabitable. Eventually, the star would consume our planet, but by that time, all life would already be gone. The black hole at the center of such stars could have contributed to the formation of massive black holes found at the centers of galaxies today. Additionally, these stars may have played a role in shaping the early universe. The powerful processes associated with these stars, such as the collapse of the central black hole and interactions with surrounding matter, could have been significant sources of gravitational waves. These waves may have influenced the formation of cosmic structures and the distribution of stars within galaxies. These stars might also have implications for astrobiology. The intense radiation from such objects could have impacted the habitability of planets in their vicinity, potentially playing a role in the development of life. In this sense, while such stars could have been rare in the universe, they may have profoundly shaped its evolution in ways we are still discovering. Although no such stars are thought to exist today, small black holes, possibly the mass of a space rock from the universe's early stages, could still be floating around. Physicists speculate that if these primordial black holes were abundant, they could be trapped within gas clouds, where new stars are born. These early-stage black holes might eventually find their way to the centers of stars. Even black holes the size of Pluto could grow immensely within just a few 100 million years, a relatively short period in a star's life cycle. Some scientists, including the late Stephen Hawking, have suggested that our Sun might even harbor such a black hole. If it did, we wouldn't notice it, even though it could be as large as Mercury. While this is unlikely, one method researchers have devised to detect these potential hidden black holes involves studying unusual vibrations in red giant stars. These stars, which are cooler than usual, may be concealing early-stage black holes at their cores. Some 500 such cool red giant stars have already been identified, and scientists are using advanced techniques to investigate whether these stars might harbor black holes. One of the most fascinating aspects of black holes is how they challenge our understanding of physics. According to Einstein's theory of general relativity, black holes are regions where gravity is so intense that not even light can escape. This occurs when a massive star collapses under its own gravity, forming a singularity surrounded by an event horizon, a point beyond which nothing can escape. Black holes come in various sizes, from stellar mass black holes, several times the mass of the Sun, to supermassive black holes found at the centers of galaxies, which can be millions or even billions of times the mass of the Sun. The discovery of gravitational waves in 2015 provided direct evidence of stellar mass black hole mergers, confirming their existence and behavior as predicted by Einstein. Supermassive black holes are believed to form through a variety of processes. One theory suggests they may grow by the merging of smaller black holes over time, while another posits that they form directly from the collapse of enormous gas clouds in the early universe. These colossal black holes play a key role in galaxy formation, influencing star distribution and the overall structure of the universe. An intriguing property of black holes is their entropy, which measures the disorder or randomness in a system. Black holes possess the highest entropy of any known object in the universe, despite their simple structure. This paradox has driven significant advancements in theoretical physics, particularly in understanding the relationship between gravity, quantum mechanics, and thermodynamics. Black holes also challenge our understanding of information preservation. According to classical physics, information about particles and their interactions should be conserved. However, black holes present a conundrum, as they seem to violate the principles of quantum mechanics. The so-called black hole information paradox remains an area of active research in theoretical physics. Recent advances in observational cosmology have provided new insights into the behavior and environment of black holes. Techniques like Very Long Baseline Interferometry, VLBI, and the Event Horizon Telescope, EHT, have enabled scientists to observe supermassive black holes with unprecedented detail. These observations confirm Einstein's predictions and reveal the powerful jets of matter ejected from black holes. The study of black holes goes beyond astronomy, raising profound philosophical and existential questions. They represent the ultimate end state of matter in the universe, where the laws of physics break down. Black holes challenge our perceptions of space, time, and the limits of human knowledge. Recently, researchers have explored the possibility of harnessing black holes for practical purposes, such as energy generation. The intense gravitational forces near a rotating black hole could theoretically be used to extract vast amounts of energy, though the technological challenges involved are immense. Looking ahead, black holes continue to captivate both scientists and the public. Future missions and observational projects, such as the Laser Interferometer Space Antenna, LISA, and advanced telescopes, promise to unravel more mysteries surrounding these cosmic giants. Black holes remain one of the most fascinating and perplexing phenomena in the universe, offering deep insights into the fundamental nature of reality, space-time, and the universe itself. As technology advances and our observational capabilities improve, we can expect more groundbreaking discoveries that will continue to reshape our understanding of these cosmic monsters.